Yeah, I'll do that.
Okay, good. Yeah, that works. Okay.
Okay. So the audio is coming from my computer right now, but I'm assuming I want to change that.
There's like a little plug on the side that you should be able to
Oh.
plug in.
Um,
And then you have to go to, yeah, you have to go to Zoom and select like a different audio.
oh, is it this?
Sorry, can you hear us?
No, I don't think that worked. Let me see.
So on your Zoom, you should be able to go to like
Yeah, I see like Cestron is the only one I see other than my
Crestron, yeah, Crestron or something like that. That's right.
okay, there's that.
And you might have to go to the like little screen and increase the volume.
Oh, I see.
Got it? Okay, nice.
Can you hear us?
Yeah.
Yes? No?
Yes. Yeah. Can you hear us?
Perfect. Yes.
Okay, great. And everything's recording. Okay, ready to go.
Yeah, okay, sounds good. Let's get started. All right, welcome. Should I start?
Yeah.
Yeah, welcome everybody. So I guess today's lecture is a little bit special. Abhishek is remote and he'll be joining us for the second part. Excuse me, I was just running like 500 meters to get the HDMI. This is what you get in the last year PhD. But anyway, yeah, so Abhishek will join us for the second part to finish up the supervised learning. And me and Patrick will spend the first half an hour to go through a Pytorch tutorial. So before we get started, maybe let's do a raise hand. How many of you have been actively using Pytorch for the past maybe 3 months? Okay, that's a fair amount. There are still some people not super familiar with that, but that's great because that's why we have a tutorial. All right, so, let me minimize this first. So in the past few years, we've seen a lot of really amazing work coming out. For example, like Stable Diffusion came out about a year ago, which is the text-to-image generator that, given a language condition, it generates like super realistic images. So this is built on with Pytorch. Another work such as Get3D, which is a work from NVIDIA about a year ago, is trying to basically from a randomly sampled latent vector generate a accurate rigid object meshes. And even a few years ago, OpenAI even had a blog post with the title of OpenAI standardized on Pytorch, which indicates like later on the ChatGPT is built on Pytorch, as well as the text to video most recent work Sora is built on Pytorch. And in addition to all the Gen AI work, we also, as robotics people in the robotics community, we also kind of like fully embrace PyTorch. For example, the most recent work, Mobile Aloha from Stanford University, they're trying to teach this robot, which is a bimanual mobile manipulator, try to cook a shrimp in this example. And also Parag, this is a work from our own PhD students from UW, Mohit, who graduated last year. And he's trying to teach a robot using a transformer-based network conditioned on the language. And also another example is Dextrim from NVIDIA about a year ago. They're trying to teach a multi-fingered dexterous manipulator, in this case is a legal hand, to do the in-hand reorientation given a image go condition. So the reason that PyTorch has been so widely adapted is because it's super flexible and it has really easy API. It's really easy for us to debug. So that's why we're talking about PyTorch today. So before we get started, we want to emphasize that a lot of contents are from blog posts we found online, as well as Sergey's 285 lecture from Berkeley. So a big shout out to those people. And if you want to find more resources, there are tons of like tutorial online too. So in today's tutorial, Patrick will spend first part to talk about Pytorch basics, functions, and modules. And then I will jump in to talk about loss functions, optimizers, and how to train your first network. All right, Patrick, take it away.
Yeah, and just add to what Zoe saying, like the reason we're doing this is because for your homeworks, you're going to be implementing like imitation learning algorithms, policy gradient algorithms, actor critic algorithms, and they all use deep learning, and they're all basically boiled down to like an optimization. So that's why we're doing Pytorch. What is Pytorch for? It's basically just solving this like optimization thing on the right. You can create neural networks, which is this F here in this optimization expression. You can do auto differentiation. You can do data sets, optimizers, GPU support. And if you look at the expression on the right, basically Pytorch can help with every step of that. So it can do the gradient descent to solve the argmin. It can create data sets and sample from the data set, which is like the summation part. And then you can define loss functions, and then you can also define your neural network. So how does it work? Basically for gradient descent, you're computing these gradients, and you're like say like you have like this example neural network with 2 hidden layers, and you're trying to do gradient descent. So you need to sort of compute the gradients of your weights of each node with respect to the loss. And to do that, you basically need to do a lot of chain rule. And Pytorch kind of helps with that by creating like a computational graph automatically of the gradients as you backpropagate from the end to the front. So you can see like when you do like .grad, which we'll talk about in Pytorch, what that'll do under the hood is compute, given like a loss function, it'll compute like the gradient of the last layer with respect to the loss, and then it'll chain roll back. So then you can compute the gradients of the second to last layer through the chain rule, and so on. So that's like a high level overview, and we'll go into like the details in a second. Any questions so far? Okay, so we'll start with like some super basics, and then we'll like go to like training your neural network with Zoe. So the super basic thing is like everything in Pytorch, you store it as like arrays or tensors. And they're different shapes. So you can start with like scalars, which are like zero-dimensional tensors, and you have vectors, which are one-dimensional tensors, matrices, which are two-dimensional tensors, and then three-dimensional tensors and four-dimensional tensors. So an example of this is like if you're storing like an image, that's going to be a 3 by h by w tensor. And if you're storing like a batch of images, that's going to be like a b by 3 by h by w tensor. So everything is sort of stored as a tensor, and you manipulate it as a tensor. So some basic like indexing things. So like, let's say we create, like if you look on the right, we can create like an array of a torch array of zeros and torch array of ones. So it's like torch.zeros and torch.ones, and we can specify the shape. In this case, we set shape to like 2 by 3. And what that'll look like is displayed on the left. It's basically creating 2 arrays, 2 by 3 of zeros and ones. And then you can do like basic arithmetic operations between them. You can multiply, you can add. In this case, we can add x and y. So 0 plus 1 is 1. And it adds it across each index. Yeah, and then moving on, let's go into like a little more complicated multi-dimensional indexing. So here, let's say we have like an array of shape 2 by 4 by 3. So what that'll look like is you have 2 dimensions here, 4 dimensions across axis 1, and then 3 dimensions down. And if we want to index into this array, we can, one example is, say we want to get the first row of the tensor. We can either do a and index 0, and then ... or and ... kind of like specifies the rest of the dimensions of the array. So in this case, dimensions 2 and 3. Or you can do 2 semicolons, and semicolon specifies like a specific dimension. So you need 2 of those. Yeah. And then you can do something else, like if you want to like index like on a different axis, like you want to index on the last axis, then you specify like the last axis. So in this case, we're trying to index the second row of the last dimension. So we do a ... 1. You can also do a semicolon 1. Yeah, okay. So that's like some basic like how do we create arrays? How do we index arrays? How do we do arithmetic with arrays? And then in Torch, they also like implicitly have something called broadcasting, which is like saying in this example, you can see we create like a 3x1 array, and then we create like a 1x3 array. And if you add those together, it becomes like a 3x3 array, because implicitly Torch, if you do something like this, Torch will like sort of broadcast the 1 into a 3. And while you can't do this, in practice, this is like one very common source of like bug where people don't cache. Like this code will run without errors, and even if you unintentionally do this, and this creates a bunch of errors. So like the recommendation is just don't broadcast. Don't like ever, always make sure like when you're doing like operations between arrays, make sure they're the same shape, unless you really know what you're doing. Any questions so far? Cool. And then some other important operations that you'll need are like shaping. So if you want to like add, in the first example, like we create like an array of 10x15. And then if you want to like add a dimension to the beginning, you can do something called like none. You can index none, and that'll basically create a new array with an additional dimension in the beginning. And then if you want to like remove like extraneous like dimensions, in this case, like it's 1x10x15, you want to remove the 1, you can do like squeeze. And then there are also ways to like transpose or permute the array, and as well as like reshape or view the array, which means like we can go through the dot view. Basically, if we have like an array of shape 10x15 and you want to like change the shape of it, you could do like, say you want to change a 10x15 array to a 15x10 array, then you could do a.view 15x10. Yeah. Okay. Device management. So there's like NumPy and Torch, and the difference is like everything. So Torch is optimized for like deep learning, so you can store things on GPU or CPU, but NumPy isn't. So everything is stored on your CPU's RAM. So that's like one difference between Torch and NumPy. And in Torch, things can either live on the CPU or GPU. And there's like an operation you can do to like move your tensor from CPU to GPU or GPU to CPU, and that's like .2 CUDA or .2 CPU. And another common error is like trying to perform operations between a tensor and GPU and a tensor and CPU. That will create the error message you see below, like expected device CPU, but got device CUDA 0. So that's also something to be careful of. In general, it's sort of like when you're training deep networks, you want to put things on GPU because it's going to be faster. Yeah. Okay. So that's the basics. After that, we have some neural network specific functions. So we're going to get into like how to create like your neural network. And one of the core components are like neural network specific functions. Like in neural networks, they use a lot of like ReLU. Actually, this should be sigmoid here. That's a typo. But so x's dot equals to torch dot linspace -3 to 3, 100 just creates. You can just think a bunch of like x values between 3 and -3, 100 of those, and then Torch has like some already defined functions like ReLU, which is a commonly used in neural networks. And if you apply that, it will like basically apply this function on top of that. So we're plotting that. In this case, instead of ReLU, we can also do sigmoid. So yeah, this should be sigmoid instead of ReLU, and that's what it would look like. Cool. So now that we know that, we can build our first like neural network module. So the way we do that in Pytorch is there's something called like nn.module, and it's like the building block for like creating these computational graphs. So an example is like a linear layer. Another example is like a convolutional layer. Those are all nn.modules. But nn.modules can also contain other nn.modules. So like you could have like one nn.module containing like many like linear layers put together. And then what's special to nn.module is there's an init function where you create your layers and create your modules. And then there's a forward function, which is like you take in the input tensors and then you apply whatever you need to apply, and then you give an output. So a more specific example of that is these two examples. One is like a linear layer, one is a conv layer. So say we have a batch size of 256, we can simply define like a linear layer. Say we want to define a linear layer that takes in like 3 features, and it has 1 output feature. And then you can also specify a number of dimensions. This is just using the default, but you can also do like nn.linear. Say you want like 3 in features and 1 out. So in this case, you have 3 in features, 1 out feature, and then implicitly a forward function is already defined. And you can just do output equals to linear layer, and then you just input a b/3 array, and that'll give you an output that's b/1 because you defined out features to 1. So that works for like flattened inputs. But if you want to work with images, a lot of people use convolutional neural networks, and that's also predefined in Torch as conv2d. So in this case, we take in 3 channels and say we want to output 1 channel, and the kernel size you also need to define for that conv layer. And a lot of images are 3 in channels, so let's set that to 3. And then so if you create like if you have like B images, that's going to be b/3 by, let's say it's 48/48 in this case. If you pass it through the conv layer, the output will be b/1 by 46/46. And it's 46/46 because like I think by default there's no padding and the stride is 1. So if you do some like math, you'll see that output is 1 by 46/46. But this is all to say like this is like the most, when you're defining your module, this will probably be like the most like basic thing you're going to be using as like your backbone. So linear layers and conv layers, as well as like ReLU functions and sigmoid functions. And let's try to all put that together. So like say we want to create like a multi-layered MLP or a multi-layered neural network using linear layers. So what we need to do is we just create a new class, and then we have to say it's a subclass of nn.module. And then the important 2 functions is init and forward. So in init, we can define all the layers that we want. In this case, we define 3 fully connected layers. And then there shouldn't be don't worry about pdb.setTrace, just like pretend that doesn't exist. But then we define the forward function, where you can pass basically your inputs through the layer. In this case, we're passing it through the first fully connected layer, then through the ReLU, then the second fully connected layer, then the ReLU, and then the third fully connected layer, and then we output that. And the way you can use such a network is, say we want to define, now we can define our network with input size and output size. In this case, let's say our input size is 2 and we want our output size to be 1. Then now we can basically do like myNet and then pass in a b/2 array, and that'll give us a b/1 output. And one important thing is like you might be asking like, why are we not doing like myNet.forward on the array? And that's just like already implicitly defined in like nn.module. If you just like don't use nn.forward, it will like automatically alias to that. And it's just, I think it's and I put that in the next slide, it's kind of best practice to do that. Just in general, like you prefer to not call the like explicitly call forward when you want to do forward. And then the other thing is the module and the input needs to be on the same device, or you run into this like if the module is on a GPU and the input is on CPU, then that's going to create the same error that we talked about before. So in this case, you can see we do .CUDA here, so we're like specifically making sure that it's on GPU as well. Cool.
Right. Thanks, Patrick. All right, loss function. So far, Patrick.
I have
Oh,
a quick
sorry.
question, Zoe.
Yeah.
When you guys are defining these conv-nets and so on, right? You have to like manually find the shape. Are there tools for you to like help deal with these shapes? Like, yeah, how easy is it to do?
Yeah, that's a good question. So yeah, you can either choose to do like the math yourself, or you can sort of define the convnet. Like I think the hard part is probably like you need after you do a bunch of conv layers, the last layer you don't know the size of it because like you need to figure out like the padding and the whatever on each layer to find like to calculate the size of the output after all the conv layers. And one way to get around that is you kind of like run a dummy array, and we can I can show like a pointer to this, but like you run like you create a dummy array and then you run it through those conv layers, and then you see the dimension of the output, and then you set that to the feature dimension after all the conv layers. Yeah.
Thank you.
Any other questions?
So what's it mean physically to have the module on the GPU? Put the data that we're inputting. The module also has to be in the GPU because I mean the weights are there.
Exactly. Yeah, exactly. So like the module is really just a bunch of like weights and biases.
Where was the line in the code where you set the modules in the GPU?
Yeah, you're actually right. So this might actually be implicit on the CPU. That's a good point. I think you'd also have to do .to CUDA here as well. So it's a good point.
After the net call.
Yeah, exactly. Yeah.
All right. So loss function. So far, Patrick talked about how do we prepare data. For example, how do we convert NumPy to Pytorch tensor? And we also talk about how do we define a neural network such as MLP or CNN and so on. And then we feed the network with our input data and hopefully can predict some values, right? But we haven't talked about how do we exactly evaluate how good the prediction would be, right? So that's why we have to introduce loss function. So essentially loss function is trying to measure how close the prediction is compared to the compared to the true or target value. So before we choose any loss functions, first step is to identify what problems you're trying to solve. So throughout my PhD life, I barely met any like other categories of problems other than those two problems. One is regression, another is classification. So for regression, can anyone give us one example of what is a regression problem? Yeah, that's a good one. Yeah, so regression, you can see that it's a problem trying to predict a continuous value and trying to define some distance function. And another classification, any examples of classification? Yeah. Dog and cat, that's a really classic classification problem. So also just some random thoughts from my PhD experience is that regression is a much harder problem to solve than classification. So if there is any way that I can convert a regression problem into a classification problem, I will definitely do that. For example, like if I want to train a robot given a image observation and try to predict a action space. So for example, it's the any-factor rotation along some like axis. So one way to formulate this is to use regression. Like you can imagine you have a CNN, then at the last part is the MLP to project into a continuous value representing a action, like a rotation in the range of like -pi to pi. But this is a much harder problem because you're essentially asking the network to have a very accurate guess of what the number is. Nowadays, people usually do is to divide or discretize the action space into like number of bins. For example, like divide this into 12 bins or 24 bins. So you basically convert regression into classification problem, and the network's essentially trying to identify which bin the rotation value might fall. All right, so since most of you are familiar with Pytorch, so I'm gonna have more questions for you. So I'm gonna list out several common loss functions and ask you what problems they're trying to solve. So first is L1 loss function. Is it regression? Nice. What about mean square error? Regression? Nice. Cross entropy, classification, binary cross entropy, classification, and KL loss. Classification. Okay, so essentially, if you see there's a loss function with a P or log P, is probably like distribution is basically classification. Oh yeah, and there's several fun facts. So if you look closely at the cross entropy, this is very special. The first is that you might find this is familiar because in the class when we introduced the objective of supervised learning, this is pretty similar because the only difference is like now you have a negative sign because now you're essentially minimize the loss function instead of maximizing. And a second fun fact is that if you expand the KL loss, you will find out that KL loss is equivalent to cross entropy just by a factor of the constant term in the first part. Okay, so let's dive into two examples to see how Pytorch implement those loss functions. So first, you need to do import torch.n, and this will have kind of like a library of implementation for different loss functions. And for example, for L1 loss, we just say n.L1 loss. And the second line or third line is basically randomly define the prediction and the true label. And you feed those two values into your predefined loss function, and then you have your loss. And for classification, such as BCE loss, you have one more extra step, which is usually for binary classification, people use sigmoid. A sigmoid is like an activation function. You project your prediction into kind of like a normalization range between 0 to 1. And for cross entropy, which is for multi-class prediction, you use softmax. People use softmax more. Okay. So after you start training your network and if you start visualizing your loss function, hopefully you can see something like this. Your loss functions, your loss value is going down as the time that you're training your network. But sometimes it's not the case. For example, you will see plots like those three, which is great because visualization is also really important to help us to debug what's going on with your training. For example, if you see your loss curve is not really going down from the beginning, then that means either your network is bad or just wrong or not big enough. You might have to switch to a much powerful network, or overfitting in the case that you start seeing the validation curve or validation losses start going up. So that means your training set is small. You probably want to increase your training data set or make it more diverse. Some other common tricks, such as sometimes you might see the loss curve is like super unstable, and you might want to try a bigger batch size or reduce your learning rate. Or sometimes you find out your loss is not really going down after a few iterations. You can schedule your different learning rate or change into a smaller learning rate after a certain iteration. Or like sometimes I found like my loss will go to none after several iterations. So this usually happens when either during your training, you're dividing a 0 or your learning rate is too high. So how exactly does loss help us to learn or help us to update the network? If we symbolize the flow of the network in the sense that if we represent the input as X and the parameters of our network is weights matrix W and bias B. So essentially we're trying to predict a label Z in the formula formulated by like W multiplied X plus B. So we compute the cross entropy loss between the predicted label and the true label Y. So our goal is to trying to find the best parameters for W and B such that we can minimize the loss. So in other words, we want to compute the gradients of the loss function with respect to those parameters W and B. So in Pytorch, it's a very simple, it's just a one line loss dot backwards. This line just computes the gradients for all the tensors for like, for example, the tensors, the matrix W or ISB, or you can also say X dot gradient and so on. Underneath, intuitively, is trying to it's using the optimization approach called gradient descent, trying to find the best parameters that can minimize the loss function. So essentially, gradient descent has two steps. One is compute the gradients, and the second is to apply one step and update your neural network, which is represented by optimizer.step. So there are three, I mean, for me, there are mostly three common optimizers that I always use. First is Atom, second is Atom W, which is super useful when you're training a transformer-based network. I found this optimizer helps a lot when you want to like have a more stable training. And stochastic gradient descent, SGD. And some common parameters are learning rates. Usually the range for learning rate is 10 to the power of -3 or -4, or weight decay. I actually barely touch weight decay. I usually use the default, although I forgot the default one is, but the range is like 0.01 to 0.05. Any questions? Okay. All right, so we're ready to build our first network. So just to summarize everything that we talked about so far. So now you're given a task. Imagine you have a data set represented by this, I don't know if it's visible to you, but there's like a blue cross here in this plot. And your task or your mission is to choose whether you want to train a neural network to the given any X, you're trying to predict the closest Y. So to summarize what we have learned so far, first, you need to define a network because this is a very simple example, which is given one dimension X, predict one dimension Y. So we're defining a linear layer. Because this is a regression problem, so we're using a MSE. And I'm going to use Atom as an optimizer with learning rate of 0.001. So usually when you're training your network, you want to train it for a long time. So you define some certain number of iterations. Within each iteration, you go through your data or data set. So here, there are 4 common steps. First is to prepare your data. This includes define your data loader with the help of like a batch size that you defined. And also, first you need to, don't forget to turn on the shuffle equals to true so that it can randomize the data sets in your training set. And usually you split the training set into training and validation with a ratio of 80-20, something like that. And the second is that, so after they train loader X and Y here, would have the dimension of batch size by whatever dimension that your data have. In this case, it's the 1. So the X will be represented as a tensor. This tensor is fed into the model that you define, which is a linear layer, and predict Y hat, which is the prediction. And then you feed this prediction together with your true label and compute your loss function, compute your loss, sorry. And after that, you do backprop and optimize, update your network. So one thing that I want to emphasize here is that don't forget to add optimizer.0grad here. This is because whenever you call this backwards, you compute gradients. In Pytorch, gradients is like accumulated. So like you want to clear out or zero out all the gradients before you compute the next gradient in the next batch. All right, so this is a very brief example of how do you want to prepare your data loader. Usually it's like init, and here you usually load your data set. This data set is often you saved somewhere on your disk. And get item is, so here usually you have several lines to process your data, and so on. Yeah. Any questions? Is it too fast or, okay, cool. Just several more things to note. First, it's really useful to do torch.save and torch.load. You should always save your checkpoints, at least every n iterations. And not only just after your last checkpoint, because sometimes if you want to visualize or if you visualize your loss plots, you found out your network is overfitting, and you want to basically check out other checkpoints. If you don't have others, you cannot do that. And you can always resume training at any time by simply doing torch.load your checkpoints. And second is that you can turn on and turn off the gradients based on if you want to use the data to update your network. For example, after you train your network for a while, you want to evaluate on your validation set or test set, you can do like with torch.no grade, and so that you won't update your network with this data. And third, logging is a really useful tool to help you to debug and visualize. The most common two tools are Weight and Bias and TensorBoard. And we also have a link which we borrow from Berkeley, Sergey's class, which is a notebook that you can interactively play with it. So super encouraging you to do this, especially when you're not familiar with Pytorch. Yeah, I think that should be it, right? Oh, and last bonus point to train your first transformer. If you have some time or capacity, really do some practice on building your first transformer, because transformer has been such a useful network. Yeah. All right, Abhishek, are you ready?
Yes. Yeah, that was great. Thank you.
Yeah. Stop sharing.
Cool. Yeah. Any questions from the class or? Okay.
Yeah, so sorry, one question.
So let's say you have access to multiple GPUs. Are you training multiple models, one for each GPU, or is there a way to use Pytorch so that it uses all of the GPUs at the same time?
Yeah, that's a great question. So Pytorch, you have like a data parallelism where it can automatically help you to do the parallelization across all the GPUs. So in the command line, you just specify how many GPUs you want to have, or like device ID, which device you want to have. Or sometimes if you want to just do your own customized like training, you want to maybe, for certain network, I want to train on device 0, some certain data I want to train on device 0. You can like go there and specify device 0 for those data. Yeah.
All right. Can everyone hear me?
Yes.
Yes. All right. Sweet. All right. Well, thanks for coming, so many of y'all, and let's keep going with imitation learning. So today we'll try and finish up the remainder of imitation learning, and on Thursday we'll start doing policy gradients. Yeah. Okay. Can you see my screen? It's all projecting fine.
Yep.
Right. Okay. So the outline of the, how many minutes? We have like 45 minutes. Yeah. So we'll try and cover a little more about multimodality and underfitting. I'll remind us what we talked about last time. We'll talk a little more about the compounding error problem and how we can fix it. And then we'll talk about a few frontiers in imitation learning and what's exciting. Okay, so the structure of our class is going to be start with imitation, then we'll do model-free, model-based, unify things, and then do frontiers, right? So we're still at imitation learning, and we really want to get into the weeds of what makes it hard and what are like solutions that people have come up with in recent years, right? So to just recap, our general recipe for imitation learning is going to say we're given some demonstrations of optimal behavior. You're going to train a policy to mimic these demonstrations using maximum likelihood. And that's the algorithm we're going to call behavior cloning, right? And so this algorithm is basically going to say, just like train a neural network or any arbitrary function approximator to map from your observations to your actions. but just by using maximum likelihood or supervised learning. Okay, so that is the basic idea. And we said that, okay, this is nice because it like reduces into a problem we know kind of works. So supervised learning is easy and it works. However, we saw that imitation learning was not supervised learning. Right? And the main issue here is that you're minimizing the loss or maximizing the likelihood on expert data, but you're then evaluating the policy when you're rolling out things under your learned policy. Right? So the issue is that your training data is under the expert distribution or D here. And your policy is being evaluated by executing under itself. So you have this issue of compounding error, where small amounts of error compound as you go longer and longer in the horizon. Right? So that is the primary challenge, if you will. Everyone with me on that front? Okay, so okay, great. So we talked about how behavior cloning has challenges in both theory and practice, and we kind of divided this into two types of challenges. The first one was underfitting, right? And the second one is compounding error. And so to remind everyone what I meant by underfitting, let's say we're dealing with a Gaussian policy, and if a Gaussian policy is used to learn behavior in this like multimodal setting where you're going to the left and the right of an obstacle, you'll get behavior that covers the modes and sends you right through the middle, right? And so we talked about how behavior cloning or supervised learning is a combination of expressivity of your function approximator. So expressivity of that theta, which maps from S star to like the parameters of your distribution, and distributional expressivity, right? So we talked about how there's different classes of distributions. Some are more expressive than others. The Gaussians are the least expressive. Other things are more expressive, and there's a trade-off between tractability and expressivity, right? And so for a Gaussian, you have this problem of mode covering behavior. And so a combination of distributional expressivity and the objective itself leads to this mode averaging problem, right? Does that resonate with everyone? Everyone remembers what we talked about last time? Any questions? Okay, so and what we discussed last time was that you can show that the maximum likelihood objective is essentially the forward KL between the expert policy pi e and the learned policy pi theta, right? And so the forward KL eats a huge penalty whenever you miss any modes, and so you have mode covering behavior, right? And this is the forward KL is a special class of a more general class of divergences, which are the F divergences, right? And an F divergence is generally defined as such. It's defined as the expectation Q of F of P by Q, right? And so you can show that if you set F equal to X log X, you'll get the forward KL. And you'll show that if you set F equal to minus log X, you get the reverse KL. And as we discussed last time, if you maintain the distributional expressivity, you say that, hey, I'm going to use a Gaussian, like that is, I want to be tractable, I want to use a Gaussian. But you change the objective from the forward KL to the reverse KL, you'll start seeing mode seeking behavior, like the one shown here on the left, like in blue. Whereas if you use the forward KL, which is normal supervised learning or behavior cloning, then you get mode averaging behavior, right? So what you kind of want here is to do things like reverse KL. But the tricky part about reverse KL is that it can often be difficult to evaluate. So the options here to fix behavior cloning. So in summary, the issue with behavior cloning is a combination of not using an expressive enough model and using a particular objective, which is the forward KL, right? And so the ways we can fix behavior cloning is either to use a different objective, which does mode seeking rather than mode covering, or we can use a richer distribution class, right? So if you use a richer distribution class, there's not a problem, but you might struggle with tractability. If you use a different divergence, that might be hard to evaluate and optimize, right? And so those are the trade-offs that you have. So the issue is behavior cloning. We're still in the issue of underfitting. So if you go back to our problem from earlier, we're saying behavior cloning has these two issues, underfitting and compounding error. Let's finish up underfitting and we'll get to compounding error, right? But the issue with underfitting is distributional expressivity and the objective, leading to this mode averaging issue. We're going to say the solutions look like either using a different divergence, which is the reverse scale, or using a richer distribution class, right? Okay, so I can't see you all, so I can't see your expression, so you have to like speak up.
There's one question.
Yes, go ahead.
What happens if we use like average of KL?
What,
Can you repeat the question, Zoe?
what happens if you use the average of KL, like
Forward and back.
forward and backward?
That's a good question. So the average of the forward and the backward KL is approximately like this Jensen-Shannon divergence, like the thing that you think of like GANs trying to optimize, and that is certainly better. So like if you use it's like a symmetric divergence, it's better. It doesn't have this like this problem, but you'll still eat a penalty for dropping a mode, right? So that has different divergence properties, but you'll still eat a penalty for dropping a mode. So you're not going to be able to just like drop a mode if you had a Gaussian. And so like things like GANs use the JSTs, which is kind of a mix of the forward and backward scale. However, they use a more expressive policy class, which is what makes them able to fit more complex things. That's a great question. Okay, so with these two ideas, we can either use a different F divergence or a richer distribution class. We talked about this a bit last time, but the idea with the reverse scale is that it's mode seeking, right? So the nice part about the reverse scale is that like the reverse scale is under this policy distribution pi. And so your policy, if you had like, bimodal distribution, your policy can choose to concentrate likelihood here, which means that it doesn't eat any penalty for missing a mode, right? And so the reverse scale is nice in that it's mode seeking, not mode covering. However, as you look at this objective, you'll see that the reverse scale requires you to know this pi e, right? And if you're just given samples from experts, like a human just goes in and collects a bunch of data, then it's like you don't actually know what pi e is, right? And so the tricky part about evaluating the reverse scale and optimizing the reverse scale is like the unknown pi e. Right? You can sample from pi theta, but you don't know pi e. That's what makes it hard. And so what Kay and others showed in their paper was that you can convert this this F divergence shown on the left. So like this is the KL divergence. You can show that you can convert it into the sample-based estimate. And the main trick is using this idea called the convex conjugate, right? The convex conjugate, I'm not going to get into it, but the convex conjugate allows you to like basically take any objective F and like write it as like a minimization problem, or sorry, maximization problem. And of this is like maximization of dx minus like this thing called the convex conjugate, right? So they use a little bit of like massaging to go from here to here. But the main trick, when you go read the paper, just remember that the main trick is using this definition of the convex conjugate, right? So whenever you have a function f, you can always express it as a minimization in terms of the convex conjugate. And that's what allows you to convert, or maximization in terms of the convex conjugate, sorry. That allows you to take this objective over here and convert it into this min-max objective. And this min-max objective is kind of how you optimize a GAN. It's like, it's often called the F-GAN trick or the F divergence trick, right? And that kind of makes this tractable because if you look at this objective, you just need samples from the policy and you just need samples from the expert. Nowhere do you actually need likelihoods. The trade-off that you're going to make, though, is that you're going to need to have to do this min-max saddle point optimization. You have to like deal with all the instabilities of GANs, right? And so generally, it's like nice to have this reverse scale as a formulation, but it can be tricky to implement in practice, even with these tricks, because you have to deal with GAN style optimization. And I've always found it really hard to deal with. Okay, does that kind of catch us up with where we were last time? Any questions?
One more
Yeah.
question.
I do have one question. Is it not possible to, given like a lot of samples from an expert, somehow get like a empirical estimate of like likelihood on
Yeah.
certain things
Oh, that's a
instead of
good
having to do all this?
The tricky bit here is that okay, you need to fit it. What you're suggesting is kind of doing density estimation on pi e, right? And density estimation typically is done with maximum likelihood, right? So yes, you can establish like a likelihood function for pi e. So you might want to do maximum likelihood on pi e, but then you might need an expressive policy distribution for pi e itself. Now you can do like non-parametric estimates. So you can do things like kernel density estimation and so on, which might help. But in general, like it's a little bit of a chicken and egg problem. As in, if I have to do maximum likelihood to get pi e to be expressive, and that is like, a rich distribution that is not tractable, then you're kind of back at the same problem, right? But yeah, it's a good idea. Okay, so let's kind of like think about this the other way, right? So we've talked about, okay, we can go from the forward to reverse scale, and that's gonna help us deal with this underfitting problem. But let's maybe try using a richer distribution class, right? So we've been restricting our consideration so far to the Gaussian distribution, right? And we don't have to be Gaussian. And Gaussian is like one type of a distribution. The reason to be Gaussian is that it's tractable, it's fast, it's closed form, right? And then you can also you can do things like reparameterization with it. It corresponds directly to the mean squared error. Like the Gaussian is good for many reasons, right? But in imitation learning, often you want to use richer policy distribution classes, right? So for instance, I'm at where I am right now is at this workshop at TRI, and they're talking a lot about how to use more rich policy distribution classes beyond Gaussians. And so this is a very active and open area of research. So the idea here is that if you have multimodal behavior, okay, the forward KL with a Gaussian is going to lead to mode averaging. But if you had a more expressive policy class, right? For instance, you have a mixture of Gaussians or an autoregressive distribution, an energy-based model, a diffusion model. All of these are different options that are more expressive than the Gaussian, right? And so essentially what I mean by more expressive than the Gaussian is that a Gaussian can only represent a unimodal distribution. Like all of these other classes are trying to represent some sort of multimodality in different ways, right? And they all have different trade-offs, and we'll cover a bunch of them. But the point here is that you're moving your distribution class itself to a more expressive distribution class. And if you're in more expressive distribution class, then even the forward KL will not underfit. Right? The consideration is that you have to make sure that it's tractable, and you can like evaluate it with samples, and it's like stable and those kinds of things. So this is like the premise behind essentially all generative modeling. So if those of you are familiar with generative modeling, like the big premise of generative modeling is how do I represent expressive multimodal distributions in a way that I can either get likelihoods from or sample quickly, right, and tractably in an unbiased way. So that's the big issue in generative modeling. And like a lot of these ideas here that I've written are just like directly lifted from generative modeling. These are just what people do in generative modeling. So let's kind of go through a few of them, and please stop me and ask me questions on any of them. So the simplest and easiest thing you can think of is rather than doing one Gaussian, you can do a mixture of Gaussians, right? So you can say that your policy distribution is a mixture with weight Wi of many different Gaussians, each with mean mu I and variance sigma I, right? And each of these are functions of your state, or in this case, your observation, right? And so these are dependent on O, maybe this is dependent on O as well. But the point here is that rather than having a unimodal thing, you can have a multimodal mixture of Gaussians. Now there's still Gaussians, right? But like with the infinite mixture of Gaussians, you can represent anything, right? And the tricky part here is like, how do you like control the number of Gaussians that you have while still remaining tractable? And so you can actually show that an infinite mixture of Gaussians is this thing called a variational autoencoder, or it's very similar. And so that's another option, right? But a mixture of Gaussians is nice usually, but it's often tricky to choose the number of Gaussians. So everything remains the same. The nice part about a mixture of Gaussians is that, your log likelihood is tractable, right? It's tractable. You can just like do gradient descent on this objective, right? You can just do gradient descent here. Everything's easy to compute, but it's often tricky to know how many Gaussians you need. That's what makes this hard. And that might be different in different states and so on. So that's the easiest and simplest thing to do. And then, people try to do other things from there. So the next thing that I really like is autoregressive discretization. So autoregressive discretization is a really cool idea in my opinion, but it's basically trying to capture the idea that categorical distributions are multimodal, right? So if you had like a categorical distribution, imagine that you had like, values A, B, and C, right? It's like naturally multimodal. It's a table. Like the table can have as many modes as you want, right? They're just like independent entries into a table. And so often the reason classification it doesn't struggle with this, right, is because classification is naturally a categorical problem. You're choosing like, is it a cat or a dog or a bird or a plane, right? And in those settings, it's like easy to be multimodal, right? And so what autoregressive discretization does is it tries to scale up categorical distributions so you can capture their multimodality. Now, can someone tell me why I can't just use a categorical distribution? So why can't my policy just be something that takes in an observation, goes through a policy, and then gives me like, a table of like different actions and their probabilities? Like, what makes it hard for me to use a categorical distribution? Can you guys help me point at someone?
This person, what's your name?
Yeah, if you have like a huge action space, it might not be possible to output everything. Like say you have like a bunch of like motors that you need to control to do some like complex grabbing action. Making a table for every little thing just might not be possible.
Perfect. So the way so most robotics problems, especially, and lots of other problems too, are continuous action space problems, right? So your action space is truly continuous, and then you can discretize your action space. So imagine your action space was a scalar, right? You can take your scalar action space and then discretize it, right? And so each of these bins is going to be like a discrete action, right? So we can call this action A0, A1, A2, but really they're discretizations of a continuous scale. Now this is fine for one dimension, right? But as Varun, right, in the front?
Yeah.
Okay. As Varun was saying, it's going to be tricky as soon as you go to like a k-dimensional problem, right? And so you have a k-dimensional problem. So imagine that you had like D bins in your first, or let's not call it D, maybe let's call it M bins, right? In your first dimension, right? And so you had M bins in your first dimension. You might have M bins in your second dimension, right? And so if you like consider if you just had to like discretize your whole action space, you're going to have an exponentially large number of bins to cover the whole action space, right? So you're going to have like M to the like D if your K, whatever you want to call it, like the number of dimensions of your action space. If your number of bins is M per dimension, you're going to have an exponentially large number of bins. And this becomes like quickly intractable. Imagine you had a humanoid and you had like even like 10 dimensions per bin, you have 10 to the 40 bins that your policy is outputting every time, right? Which is like kind of crazy. And so what the autoregressive discretization model does is it tries to convert this M to the D problem into a linear problem. So it's like M times D problem, right? And so that's what makes it really cool is that it allows you to use categoricals, but it does it in a way that doesn't scale exponentially. And the idea behind autoregressive discretization is to do discretization step by step. And so the math goes like this, right? Imagine that you had 3 dimensions, let's say A1, A2, and A3, right? Let's say given some S. Now you can always write this using the chain rule of probability as A1 given S times A2 given A1 and S times A3 given A2, A1, and S, right? This is just like the chain rule of probability. And so now what autoregressive discretization does is it parameterizes each of these distributions as a categorical distribution, right? So each of these is categorical, right? Which is nice because each of these now is like multimodal. It's easy to discretize, but the important thing is that you discretize every bin independently, but you like, just like a transformer or recurrent neural network, it's like you sample from the first thing and then you like feed it into the second thing. And then you sample from the second thing and then you feed the first and second thing into the third thing, right? And so the point is that you can discretize M dimensions per bin, or M bins per dimension, and just have like them be completely separate, which makes it not exponential, it makes it linear. Right? So you have M times D bins, right? But you're just going to do sampling from the first dimension, feed it into the second dimension. Sampling from the second dimension, feed the first 2 into the third dimension, right? And so you can kind of like the math over here kind of explains what's happening. So in the first step, you sample the first dimension. Then you're using a neural net or a function approximator. So you're going to take the sample from here and you're going to like stick it into the second dimension. And then you're going to take the sample from here and you're going to stick it into the third dimension. And that's how you're going to do sampling, right? But the point is it's multimodal because each of these distributions themselves is a categorical, which makes the joint distribution a multimodal distribution, right? So it allows you to, you can think of it as like, you have like dimension 1 and you have like a categorical, and then you have dimension 2 and then you have a categorical. And so you can like represent arbitrary multimodal distributions in 2 dimensions, right? And so that's what makes it nice. This is going to be on your homework, so please ask me questions here if you didn't understand or if you
One question was,
go ahead.
So, different from large language models, you have to remember the past, right?
so
Essentially, you have to remember the past observations that you took. But
Yeah.
Is there any way to, I guess, simplify or in a way save that, like, because the dimension is like 1,000, then you have to run, like, save 1,000 data.
No, yeah, that's a great question. So usually what you're going to do is like literally what we've written on this block, on this figure here, right? You're going to like use a recurrent model like LSTM or a transformer. And so you don't have to like, I mean, a transformer still has to, but like, let's say use an LSTM, you can like use the recurrent state to remember all the previous things. And so you don't need to like literally carry across all the previous actions, right? So just like the way you'd implement these models would be something like the way you're going to do in the homework is simpler, but like if you want to do it with, like at scale, you would do it with a recurrent model. Yeah. Okay. I'm going to keep moving for the sake of time, but yeah, I really like these models. I think they work surprisingly well. And so play around with them. There's a class of models called energy-based models. And the whole idea of an energy-based model is that you can represent the likelihood of a policy as a normalized exponential negative energy, right? So it's saying that like, imagine that you had like an energy function, right? So you have like, let's call this like A. For a particular O, you have like an energy function, right? And it's saying that an energy function is a scalar, but to get the likelihood function, you're just going to take the exponential negative energy and you're going to normalize it by the integral exponential negative energy, right? That's the definition of an energy-based model. And the reason energy-based models are interesting is because if you define things as energies, right, you can define an energy function, and your energy function can be, let's try and draw it here. The energy function can be something like, right? So let's say you had like two, like, you can think of this as like the policy has highest likelihoods at states that have the lowest energy, right? So if you look at this energy function, it's proportional to the exponential negative energy. So things that have the lowest energy have the highest likelihood, right? And so because you're parameterizing an arbitrary scalar, like that scalar is just like a function, right? It can have things like, it can have multiple modes really naturally, right? And so that's what makes it nice to like parameterize multimodal distributions. What makes it tricky is that you have to compute this like normalizing factor. And the thing that's hard is that you have to integrate this over all possible actions. For it to be like a valid probability distribution, you have to like normalize it, right? And so energy-based models are great, but they're like kind of hard to use. Some folks at Google have like shown that it can be done. So you can show here on the right is an energy-based model and on the left is behavior cloning. So you can see that when done right, it can be effective, but it's often hard to train, right? Because of this like normalization, like you often call this a partition function, right? The partition function is hard to compute. The partition function being this denominator here at the bottom. And so that kind of brings me to the next thing, which is, I think, a lot more scalable, which is diffusion models, right? And people have different views on diffusion models. The one that people often think of is, okay, you take a thing, you noise it, you denoise it, right? And you can think of the same thing for policies, right? You can say that what you're going to learn is a function that takes in like an O and then tries to like go from a noisy sample of N of A to like an optimal A, right? And so you like learn this denoising process that takes you from like a sample from a Gaussian to like a valid action, right? The view that I like to take on it is the score function view. So you all should look up this author Yang Song. He does really cool work. But he has this idea on score function, score functions and diffusions, and they're kind of related. But the way that I think about it is you can think of score functions, as rather than trying to estimate the probability or the log probability, you try to estimate the grad log probability. Right? And the reason it's nice to estimate the grad log probability is if you go to the previous slide and you say that, okay, our probability is proportional to exponential, whatever, negative energy, AO, and divided by some normalizing factor, right? When you take the gradient of the log prob, the denominator goes away, right? So you can write this as grad A log of exp minus E minus log Z, right? But Z is a constant with respect to A because you're integrating over all the actions, which means that when you take the gradient with respect to A, the denominator goes away, right? So the denominator going away is great because you don't have to compute this partition function. And so the way that I like to think of diffusion is just like it's a really nice, clever trick to be tractable when it comes to computing these energy-based models. And energy-based models are really nice because they can be arbitrarily multimodal. Right. So I mean, I find that intuitive. So I'd recommend reading some of Yang Sang's work to get intuition there. Any questions? So the main point I want to convey is that we need to go from Gaussians to more expressive probability distributions. They're not always tractable like in energy-based models, but with tricks like diffusion models or autoregressive discretization, they can become more tractable, right? Okay, any questions before I move on? Okay, great. I'm expecting everyone to ace those homeworks then, huh? All right. So the main consideration is you want to balance tractability versus expressivity and computation, right? But let's keep going back to our roadmap. And we've said that, okay, we've dealt with underfitting. We can either change the forward scale to a reverse scale, or we can use all these like fancy generative model things. We can use autoregressive models, or we can use diffusion models and things like that. Right? And so we've kind of found a way to deal with underfitting. We've said, okay, we're going to either use a richer policy class or an alternative divergence, right? So at least we have some handle on this problem. And let's think about the compounding error problem. So the compounding error problem, just as a reminder, is saying that when you go longer and longer in your horizon, you're going to like make little errors. And so you're going to have like deviation, which is quadratic in horizon, which is what makes it tricky, right? And so with compounding errors, we need to find a way to like take this like quadratic dependence and try to make it linear or sublinear, right? That's kind of where we want to get. And so let's start by thinking about like, let me start with an empirical example. Let's start with the like an example from self-driving, right? So people back in 2016 did something that maybe we think is crazy, which is doing imitation learning with neural networks on a car, right? This is in Santa Clara. The NVIDIA team did this, but they actually just did imitation learning on a car where they had people demonstrate a bunch of stuff. And this is what happens with standard behavior cloning, right? It like kind of runs into stuff and it's like swerves and does crazy stuff, right? So their initial attempts at doing this were not very successful, right? And so you can see here that they like weren't very successful in doing so. But after, they did a clever little trick, and after significant amount of data collection and this clever little trick, they were able to do a lot better. Like I wouldn't say it's roadworthy still, but they're able to do a lot better, deal with these compounding error issues, and drive over long horizons, right? That's the important bit. And so yeah, before I tell you what it is, does anyone have a guess on like what this trick might be to deal with compounding error in this autonomous driving setting?
Adding noise.
Yeah, it's essentially adding noise, but in a kind of clever way, right? So let me walk you through it, right? So the way they did it is that they had 3 cameras, right? So they had one camera facing front, another camera facing left, another camera facing right. So they had this front camera, which is like the main one for driving. And then at data collection time, they had a left camera, and then they had a right camera. And so what they did is that they like collected images. They collected the left camera images, labeled them with swerve a bit to the right. And then they collected the right camera images, said swerve a bit to the left. And then they collected the middle camera images as regular actions, right? And then they just like added these all to the data set, and then at inference time, they only ran with the middle camera, right? And so what they did is for every data point that they collected, they essentially got 3 data points, right? And so the nice part about that is that you can get like essentially corrective data. So it's like saying that if your car had been facing to the left, as in if the middle camera had been facing to the left, you need to go more to the right. The middle camera had been facing to the right, you need to go more to the left, right? Which I thought was super clever. But essentially, it's like getting corrective labels that bring you back just by being clever about their data augmentation, right? And so whoever said adding some noise, that's essentially what they were doing, but in like this kind of clever way. And so the general principle behind a lot of these like methods that deal with compounding error is to like augment the data set in a clever way that brings you back in distribution, right? So if you see the distribution here shown in red, you really want things that bring you back in distribution, that take you from this out of distribution state and bring you back in distribution. Like that's really the trick, right? And so whenever you want to do things with compounding error, you want to find ways to stabilize back to being in distribution. And so like essentially all of the things that have been successful try to take these out of distribution trajectories and try to provide either corrective labels or corrective policies or this clever data augmentation that brings you back in distribution. And by bringing you back in distribution, if you remember what happens with Dagger, you fall off the cliff, right? So if you're, or not with Dagger, sorry, with behavior cloning, if you fall off the cliff, you never come back, right? So if you recall what we had with our figure over here, right? If you like, let's say you made an error, you fell off the cliff and you just like keep eating error after that, right? And the important thing is that what we need to do is we need to make sure that we have things that bring us back. Even if we fall off, you make one mistake and then you come back. And so you don't eat like the whole time horizon of mistakes, right? And that's going to bring you from quadratic to linear. And that's basically the whole trick in all of the next section. You just want to find things that bring you back to the data one way or the other. So it seems like a simple idea, but it's often kind of hard to do. And it's like very powerful in that it like really, really improves the performance. And so mathematically, what it means is that if you have like P data, which is your training data, and you have P pi theta, which was like the data that you collected under your policy, really what you want to do is try to make P data similar to P pi theta, right? Because if P data is similar to P pi theta, then your policy doesn't freak out, right? There's different ways to do this, but the simplest way to do it is to try and just like convert P data to P pi theta, right? And so this is a simple algorithm called Dagger. And the key idea of Dagger is trying to say, can we like expand our data set to include the states that the policy might visit when it has this compounding error? And can we find ways to correct the behavior in those settings, right? And so, so the key idea is very simple. It's going to say you're going to collect training data from P pi theta, and rather than doing behavior cloning, which says I'm going to just like take expert data and imitate it, what Dagger does is it says I'm going to take expert data, imitate it. Then I'm going to take my policy, run it in the environment, collect more data, but with expert labels, add it to my data set and repeat, right? And so this might just seem like collecting more data, but it's important that you follow this following procedure, right? So you start by training pi theta from some human data, just with behavior cloning, plain old behavior cloning. Then you're going to run pi theta in the environment. You're going to actually like execute it, right? And the execution is going to give you a bunch of states that the policy visited, right? So like imagine that, imagine that you had your training data, and let's say you did behavior cloning and your behavior cloning visited all of these states, right? Now, this dpi in the second line is basically these states that are visited by the policy when you're executing, right? And then what you're going to do is you're going to ask a human or an expert to label these observations with expert action. So let's say you're here, you drifted off. You're going to like ask a human to go to each of these states and then label what you should have done, right? So like the important thing is that you're going to run pi theta in the environment. It's going to give you your data. So pi theta is the one that is not good enough yet, right? So you're going to get this other data. So let's call this expert. Let's call this pi theta, right? You're going to get these other states. And then on the states that your policy visits, your imperfect policy, you're going to ask an expert to label them. Right? And so an expert is going to label them. You're going to like take this extra data, which is basically, you know, O1, A1 star, O2, A2 star, etc. You're going to add them back to your data set. And now your data set is expanded. So it's called Dagger or data set aggregation because you're just aggregating data over time. Right? And so you're just saying, okay, it's kind of like whack-a-mole, right? You're saying, okay, I trained it this way. Then I'm actually going to deviate here, but now I'm going to add this to my data set, but I'm going to like provide corrective labels that bring me back in distribution, right? And then I'm going to repeat. And so the whole idea of Dagger is just
Sorry,
that,
one
right?
question.
Yeah, go ahead.
It seems like this could be something I would imagine be applied in, I guess, the municipal state space. Like I guess like a Carson or like for example, but like I would imagine like with a lot of states or like a complicated couple system like a robotic system, how would an excellent system handle that?
Yeah.
Can
Did you
you
get the
repeat-
question?
Now, can you repeat that for me, Zin?
Yeah, so how do we apply the Dagger for a lot of complicated system in robotics, a lot of tasks in robotics?
Yeah, no, that's a great question. So if I'm understanding correctly, it's basically your question is, imagine you had a complicated system and you're asking a human to go back and label the expert action in those systems, right? And you can't like just arbitrarily set the systems to whatever you want. So I think there's two strategies that people do, right? One, which is post hoc labeling, right? So in some cases, you have a drone or something, you know, if you need to go left or need to go right or whatever. And so people do post hoc labeling, but that only works for simple systems. What people often do is they do blended control, which means that like it's kind of like a safety driver in a Waymo car, right? Like it's like you do blended control where you run the policy for a while and then you give control to a human, and then you run the policy for a while and then you give control to a human. And so you can derive the same bounds that you have in the Dagger algorithm when you have blended control. And so that's typically what people do in settings like driving and so on, is that they like alternate control between the robot and the human, right? And that allows it to like blend together. So you're like providing data on the fly. Does that answer your question? Yes? Okay. Okay, so that's the Dagger algorithm, right? You can actually show that it is sublinear in regret, right? And essentially this figure kind of explains what's going on. You like want to navigate this way, you deviate, you provide corrective labels. Now you have a better data set. So you're going to like avoid those mistakes. You might still make other mistakes, but you'll add those to the data set and you repeat, right? And so there's this really nice paper that they wrote at CMU, Ross et al. In 11, which basically argues that this Dagger tile algorithm is like an online learning no regret algorithm. And so it shows that essentially this will converge at a linear rate. And so that's good. So data set aggregation is good and it works in practice, right? So if you have a drone, you can see that this is actually with Dagger. And you can actually fly it around in a forest, and they weren't able to do this without the Dagger algorithm using this kind of blended control thing that I mentioned. So Dagger is great, but as someone acutely pointed out, right, like there's a couple of issues with Dagger. The first is that it's hard to like reset a system or ask a human to go in and post hoc label a system, right? And so it's difficult to get these like labels. And secondly, it's often hard for a human to even provide labels for a complicated system, right? So it's like, say you have a humanoid or something like that, it might be hard, or like, especially if it's not anthropomorphic, it can often be really hard to provide labels, right? So these two issues persist. The first being collecting data at data collection time, and the second being generating corrective labels without having to have a human do it all the time, right? So I'm going to rush through these real quickly, but the first thing we're going to try and deal with is we're going to try and deal with avoiding requiring the human to come back at, after the fact. And all we're going to do is we're going to force the human to provide corrections during training time. And so there's this algorithm called DART, which some folks at Berkeley proposed, which is, I think, really clever. All they did is that at training time, when you're doing behavior cloning, just add a little bit of noise. And like they have all this theory to like choose the noise levels and so on. Like in practice, all you really need to do is like add a little bit of noise to your data collection. And when I say a little bit of noise, let's say you're like doing teleoperation, right? So you're like let's say your system was down here, right? You commanded this action over here. All you're going to do is when you like actually command it to the robot, you're not going to command exactly what the teleoperator said you should do. You're going to like command a slightly noisy version of it. So it's a little counterintuitive. You're going to like reduce the accuracy of the system a little bit. So you're going to introduce a little bit of noise at training time. But what that forces is that the demonstrator now has to like be in this state and provide a corrective label here. Right? And so essentially all you're doing is you're like forcing there to be some noise during data collection. And this noise during data collection widens the set of initial state or widens the set of states that you see. So you form kind of like a tube around the optimal, which like keeps bringing you back, right? So there's like a lot of theory on this, and like there's a lot of contraction theory, and there's like tube MPC, and there's like a lot of like real hardcore theory about this. But in practice, if you ever want to do this, just remember to like add in a little bit of noise during data collection. And a human is a great stabilizer, as in a human will provide corrections, right? So you want to like maximize likelihood, but you want to do it while providing noise during data collection. And that's it, right? That tends to work super well. They applied it to a bunch of different problems. We've applied it to a bunch of different problems. In general, it's like good practice. Whenever you're doing imitation learning, add a bit of noise. It'll make your life way better. Right. So that's the first idea I thought was good, but it doesn't always work, right? So here's an example from our student case, where she tries to do fine manipulation. She's trying to pick up screws from this bowl. Now, if your like robot is jittering when you're like picking up things from a bowl, like, it's not going to work, right? And so it can be tricky to apply this in all settings, right? Just applying noise. And so in those safety critical settings or settings where you have to have high precision, it can often be difficult to just add some noise to the training set. And so in those cases, you have to do something a little more clever. And so the idea here is very simple. It's related. Again, it's all the ideas are related. You're still trying to provide corrective labels. You're still trying to go back to the data, but rather than have a human do it, you're going to try and obtain these corrections from a learned model of how the world works, right? So if you remember our definition of an MDP, we had like this transition dynamics P of ST plus 1 given ST and AT, right? Tells you how the world transitions. What you can do if you have an approximate transition model, P hat of ST plus 1 given ST and AT, you can use that approximate transition model to figure out a label that brings you back. Like, for instance, if you knew how the world transitioned with different actions over here, right? You can say that actually the action A1 brings you back to the data. And hence you want to add that to your data set, right? So if you have an approximate dynamics model, you can use that to provide these corrective labels. And so that's the key idea to like avoid having a human in the loop, is that if you have an approximate dynamics model, you just want to find, you know, a set of states and actions that bring you back to the data, right? And that's the key idea in the next line of work. I'm going to skip the details, but some examples that I think are cute are doing things like behavior cloning for fine precision tasks. You can see when you add these corrective labels, it does a lot better. You can do things like picking up a coin, which is like extremely precise, right? And these kind of deviate a lot unless you add these corrective labels. But really the point I want you to take away is whenever you want to deal with compounding error, try to find corrective labels that bring you back in distribution, right? Okay, so I think we're out of time, but the rest of my stuff is on the slides. We'll start policy grade next time, but I'm looking forward to seeing all of you on Thursday. All right.
Thanks, Abhishek.
Thank you very much. I have a quick question. Is the homework, like, they were talking about the homework, but is it out yet or no?
It's not yet. We're going to release the end of next week.
Okay, cool.
So
And
it's
just
2 weeks for homework. For each homework, you have 2 weeks.
2 weeks of homework. Okay, thank you very much.
Yeah, no problem.
All right. Cool. Thanks,
You
bro.
guys.
Yeah.